In this video, we would like to introduce basic properties of the general exponential function and the general logarithmic function, that is, with a base other than e. And then in our next video, we will talk about the associated differentiation and anti-differentiation formulas. Now, these should be common ideas, so just a reminder from what you've encountered in past courses, especially pre-calculus, maybe algebra. So here it's maybe defined a bit differently, but we're saying a to the x, and we need a to be positive, is equal to e to the x ln of a. And noting that the a is inside the natural log is a good idea of how we remember it has to be positive. But in terms of what the graph would look like, it does depend upon the size of a, 0 to 1, equal to 1, or bigger than 1. If a is between 0 and 1, the graph is going to look something like this. So you're going to go through the point 0, 1, and you're also going to go through the point 1, a. If a is equal to 1, that exponential function is just going to end up being the line y equals 1. And if a is bigger than 1, what we are going to end up with is a graph that looks like this, where you're still going through the point 0, 1, but when you plug in 1, you get out a. So we have this point 1, a, and now a is bigger than 1. So when a is bigger than 1, the function is increasing. When a is between 0 and 1, it's decreasing. And there are, of course, several limits that you can note as well. In the case where it's decreasing, we can see as x goes to infinity, the curve is going to 0. And when x goes to minus infinity, it's going to positive infinity. Similarly, in the increasing case, as x goes to minus infinity, the curve's approaching 0. As x goes to infinity, the curve's blowing up to infinity. Now, all of the basic properties that we discussed associated with the exponential base e are also satisfied here. So if you were to go ahead and replace the a's with an e, you would see similar properties. I will let you pause the video and study these if you would like. We can also, for a positive a value, define the logarithmic function with base a, and we just define that to be the inverse of x equals a to the y. So in terms of x equals a to the y, and for fun here, I'm going to think particularly in the case where a is positive, or excuse me, bigger than 1. And when a is bigger than 1, we saw that that graph, y equals a to the x, looks something like this. And 2 points in particular that we know are on this graph would be the point 0, 1, and the point 1, a. Because we define log base a to be the inverse of this function y equals a to the x, graphically, it would be the reflection about this line y equals x. So the graph of log base a is going to look something like this, where we would have the corresponding point 1, 0, the corresponding point a, 1, and this is the graph of y equals log base a of x. So a few basic properties. So the similar properties that we've seen before, but kind of just reminders from a pre-calculus class. So log base e is really the natural log. Log base a of x, think the change of base formula, can be written as natural log x over natural log a, which, as a reminder, if we can differentiate the natural log, 1 over ln of a is a constant, we should know the derivative of log base a. You can break it up over addition and make it a sum, break it up over division and make it a difference, and a constant out front can be brought inside as a power. So let's just look at a few basic examples. The first one, we're just going to solve for x. So restating this, we can say that log base 8 of x equals 2. So that 2 that we get out would be the exponent that we have to raise 8 to in order to get x. So the equivalent statement here would be that 8 to the 2 is equal to x. So the value of x is 64. In the next example, solving for x, it was hopefully a familiar type of problem. We did simplification similar to this in a previous video. We can combine on the left-hand side and think of this as being the ln of x times x plus 1. So x squared plus x. So when you combine two natural logs with addition, what you do is multiply together the insides of those natural logs. Now we use properties of the inverse. So we know the inverse of the natural log is exponential. So e raised to the ln of x squared plus x should be e raised to the 1. So e to the natural log cancels, and what we have is x squared plus x is equal to e. So x squared plus x minus e is equal to 0. So this equation involving logarithms boils down to solving a quadratic equation. But a warning to go along with this, if we look back at the original equation, it involved a natural log of x. In order to plug an input into the natural log, what we need here is x to be strictly positive. So let's keep that in mind, and I note that because when we solve the exponential, it's possible we could get a negative solution. So by the quadratic formula, we have x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2 times a. So we would have x is equal to minus 1 plus or minus the square root, and note that this was really a minus e in here, square root of 1 plus 4e, all divided by 2. Now, because of this plus and minus, this is really describing two possible solutions. The problem is the solution corresponding to the minus would give a negative value of x. So I'm going to cross that off, and because we need x to be positive, our only solution would be minus 1 plus the square root of 1 plus 4e divided by 2.